Okay, so I did record a review over the break, so I don't know if you guys saw that or not. I should have sent out an email to everyone during the break, so then you guys know that I did record a review and I posted the recording to our YouTube channel already. So in that review, I talked about like eigenvalues and eigenvectors and kind of like definitions and how to compute them. I'm going to continue doing that today and going over like some more of like theories and things that you need to know. Okay. So let's first quickly recall the definitions of eigenvalues and eigenvectors. Okay. So okay, let's say we have a square matrix A. Okay. All right, so we see that lambda is an eigenvalue of A if there exists a non-zero vector x such that A times x is equal to lambda times x. Okay. Okay. So then that's definition of an eigenvalue. So here lambda is the eigenvalue. It's going to be a scalar quantity. So it's not a vector, but a scalar, a number. And then the vectors x satisfying this equation would be like the corresponding eigenvectors then. Okay. We talked about how to calculate eigenvalues and eigenvectors last time, so I'll just remind what the procedure was. So the first thing you're going to do is calculate the eigenvalues. And you calculate the eigenvalues by computing the determinant of A minus lambda I, setting that equal to 0, and then solving for lambda. Some people like to do lambda I minus A instead of A minus lambda I. That is also acceptable. Okay. So you take these equations, you solve for lambda to get the eigenvalues. Once you have the eigenvalues, to get the corresponding eigenvectors, you look at the null space of A minus lambda I, or you could look at the null space of lambda I minus A instead, so one or the other. But you find the null space of A minus lambda I. We call this the eigenspace of A, corresponding to the eigenvalue lambda. And essentially the non-zero vectors in this null space would constitute the corresponding eigenvectors. Okay. So we will do some examples of calculated eigenvalues and eigenvectors again. But before I get to those examples, I want to talk about one of the main applications of eigenvalues and eigenvectors. So the main application is that we can use eigenvalues and eigenvectors to sort of diagonalize square matrices, okay? Assuming that they have enough eigenvectors. And so when we talk about what this diagonalization is, what's the idea of it, kind of how it works, okay? And just kind of real quickly before I can explain it, I want to recall a little bit about matrix multiplication first, okay? So I'm just going to review the 2 particular facts regarding matrix multiplication first. So the first fact I wanted to recall is when you're multiplying 2 matrices, so let's say I'm multiplying a matrix A with a matrix X, okay? And let's say the first column of this matrix, I'll call the first column X1. Okay. The second column, let's say the second column is X2, and then so forth, okay? All right. So when I multiply these 2 matrices together, the product, its first column happens to be A times X1, the first column of X. Okay. The second column of the product happens to be equivalent to A multiplying the second column of X, X2, and then etc. Okay. And I'll just kind of do like a really small example with a 2x2, just so we can understand this. Maybe I'll set up the example like this. Okay. So what I'm saying up here is when you multiply these 2 matrices together. So let me just compute what the first column of the product would be first. Okay. So when I'm computing the matrix multiplication, so we would probably do like A times X1 plus B times X2. That would be the first entry there. And then we would do like a C times X1 plus D times X2, and that would have been this entry. Okay. And this would be the first column of the product, and then we'd multiply this with everything here to get the second column, right? Okay. So this first column of the product was, all we essentially did is we took the matrix A, B, C, D, and we just multiply it with the first column of this matrix, and that gave us the first column of the product, okay? Likewise, like A times the second column here will give us the second column of the product. So that's kind of what I was talking about up here, okay? And then just one more kind of observation I wanted to make regarding matrix multiplication. Okay, maybe I'll start with the example first, and then we'll kind of write out like a general, like sort of formula for what I'm trying to say. So if I take a matrix and I multiply it on the right by a diagonal matrix like this, okay? So I guess I'm going to illustrate with this 2x2 first now. So if you do the multiplication, you're going to get A times lambda 1 plus 0. You're going to get next to 0, and then B lambda 2 for this entry. And then C lambda 1 plus 0. And then you'll get 0 plus D lambda 2. And so when you look at the product, what I want us to observe is that the first column of this product, it was lambda 1, whoops. Okay. So it was lambda 1 times the first column of, if I call this A, okay? And then likewise in the product, the second column happens to be lambda 2 times the second column of A, okay? So I guess in general, if you have, let's say you had like a matrix X, again, let's say its first column is X1, let's say its second column is X2 and so forth. When you multiply on the right by a diagonal matrix, the result of the product, the first column of the product will be lambda 1 times the first column of X. So just be like lambda 1 X1. The second column of the product of these two matrices would be lambda 2 times the second column, and then so forth. Sure. All right, so then those are just some of the observations I want to make with matrix multiplication. And now to see how this ties in with eigenvalues and eigenvectors. So let's say that we have, our n by n matrix A. And let's say we have the eigenvalues. Lambda 1, lambda 2 through lambda n. So let's see, these are the eigenvalues of A. And then let's say x1, x2, and so forth. These are corresponding eigenvectors. Okay. Okay, so that means A times x1 would be equal to lambda 1 times x1. Ax2 will equal lambda 2 x2, and so forth. Okay. All right. Now, if I take the eigenvalues and the eigenvectors, and let's say I put the eigenvalues into a diagonal matrix. This symbol here is a capital lambda. So these are kind of like a lowercase lambdas. This is a capital or sort of an uppercase lambda. Okay. I still pronounce it as lambda, I guess. Yeah, I think so. Yeah, at least I'm actually not sure. So I don't know if there's like another way to read it actually. Um, yeah, I've always kind of known that. I always just kind of understood it to be a capital version of lambda. That's how I've always understood it. I can see that. Yeah, right. So maybe if I wanted to emphasize it, I would maybe say capital lambda instead of just lambda. But that's probably what I would do. Yeah. And then likewise, let's take the eigenvectors and let's also put them into a matrix. So like the x1, the first eigenvector is the first column. X2, the second eigenvector is the second column, and so forth. Order is not too important most of the times. Uh-huh. No, not particularly, yeah. There's one application of eigenvectors and eigenvalues where there's sort of a preference to order the eigenvalues from largest to smallest. That application, something called the singular value decomposition. I don't think you guys are really going to get to it this semester. At least that's not, it doesn't look like you will really. Or if you do, I don't think you would see like a question on it. Like to me, it's maybe something they might just squeeze in at the very last lecture, maybe. But from what I've kind of seen, like based off like the assignments, I guess, it doesn't look like they're really going to get to it this semester. Okay. Yeah. So for singular value, and it's not like, I guess like in practice, there's a preference for ordering the eigenvalues from largest to smallest when you're doing this singular value decomposition. So essentially the largest ones are kind of like the most important ones, is sort of how it works with this application. So you order them from largest to smallest, and then for like the really small ones, if they're like really small, you can sometimes just kind of like ignore them because they're just like not relevant. And yeah, that helps. So I can do a brief detour. So singular value decomposition. One of its applications is to sort of like so if your matrix is storing like some data, singular value decomposition is kind of one way of like compressing the data by like removing some parts of it, like removing like kind of the parts that are somehow like least important. A little bit, yeah. So I guess like the parts of the matrix that correspond to like the smallest eigenvalues um, are sometimes like kind of like omitted, if you will, or just kind of like deleted or removed. And that way you kind of retain most of the important information, but you've also removed a lot of like the fluff. And that kind of helps with, I guess, like saving on like memory and things like that for like storing the data. So image compression uh, kind of uses SVD for that, or at least like some versions, I guess, of image compression will do that. So like for the matrix, each entry of the matrix will represent like one of the pixels of the image. Um, so the number will tell you, I guess, like maybe like the color or the brightness or something like that of that pixel. Right. And then you can use SVD to compress the image without losing that much quality because you're only removing like the stuff that's not important or like not significant. Okay. Yeah, so that's kind of one of the applications of SVD. And so in practice, for SVD, it's useful to order the eigenvalues. Now, I guess in theory, for SVD, it's not important whether you order the eigenvalues or not, though. But like how it's used in practice, people tend to like to order them. Okay. Mm-hmm. Mm-hmm. Uh-huh. Uh-huh. Yeah. So each of the eigenvalues will have their own like corresponding eigenvectors. Yeah. So yeah, so like the like x2 doesn't necessarily correspond to lambda 1 in any way, for instance. X2 corresponds to lambda 2 specifically. Yeah, yeah. That's true. Yeah, yeah, yeah. That's right. Yeah, yeah. Okay, so when we look at the kind of observations that we made earlier regarding matrix multiplication, if we take matrix A and we multiply it by this matrix of like eigenvectors. Okay. According to what we talked about up here, the first column of the product would be A times x1. The second column of the product would be A times x2, and so forth. Now, however, though, since these are specifically eigenvectors of A, with corresponding eigenvalues, lambda 1, lambda 2, this product that we have here, we can rewrite it as ax1 should be equal to lambda 1 x1. Okay. And likewise, like ax2 should be equal to lambda 2 x2, and so forth. Okay. All right, but then this expression that we have here, it's equivalent to multiplying the matrix X with the diagonal matrix capital lambda on the right. Okay. So that's kind of what we observed over here earlier. So when you like multiply on the right by this diagonal matrix, it multiplies each of the columns by lambda 1, lambda 2, and so forth. Okay. So you end up with this kind of equation that A times this matrix of eigenvectors is equal to the same matrix of eigenvectors, and then multiplying this diagonal matrix of the eigenvalues. Okay. Now this is actually not super important or super useful by itself right now, but rather if this matrix of eigenvectors X, if X is invertible, then we can kind of move the X over to the other side by multiplying by its inverse. And that leads to this factorization. The A would be X times capital lambda times X inverse. Okay. And so this factorization has many uses. So we have kind of a word for when a matrix can be factored like this using the eigenvalues and eigenvectors. So we say that if you have a matrix A and it can be factored, in this form, where this matrix in the middle is specifically a diagonal matrix. Then we say that the matrix A is diagonalizable. Yes, so it should be, okay? So if matrix A can be factored as such, with diagonal matrix in the middle, then we say that A is diagonalizable, okay? Right, that's right. And here, what we've kind of seen with this discussion up here is that for a matrix A to be diagonalizable, so it's based off the eigenvalues and eigenvectors of it, okay? Sorry, what was that? Yeah, so not every matrix is diagonalizable. Let me touch on that real quick, and then I'll get back to your question. So one of the keys for making this work, though, is this matrix X had to be invertible, right, in order to make this happen. So for a matrix to be invertible, its columns have to be linearly independent. Okay. So you kind of get this observation from what we did up here, that for a matrix A to be diagonalizable, let's say it's an n by n matrix. It'll be diagonalizable if and only if it has n linearly independent eigenvectors. Okay. So then if you had these n linearly independent eigenvectors, you could then create this matrix X, which will be invertible, get the corresponding eigenvalues, and get this factorization. Okay. That's right. Yeah. Okay. So then in my last video that I did last week during the break, we did see an example of a matrix that did not have enough eigenvectors. It's this one over here. Yeah. So for this matrix, what happened is, in this example, we calculated the eigenvalues, and there's only like one distinct eigenvalue. Okay. So like lambda equals 1 was an eigenvalue, like with sort of like a multiplicity of 3, if you will. Okay. Right, right. When we found the eigenspace, the eigenspace turned out to be one-dimensional. So we had just this one vector as a basis for the eigenspace. Yeah, so this matrix is not diagonalizable because of that. It only has like one linearly independent eigenvector instead of the necessary 3. Okay. Are you looking up here? Okay, over here. Okay, okay. So let's see here. So when we did a minus lambda I, so that subtracts lambda from the diagonal entries. And this is a triangular matrix, so its determinant is just its product of its diagonal entries. So that's how we got this straight away. And that's how we got just lambda equals 1 as the only eigenvalue. Mm-hmm. Yeah. So I guess like once we got like the eigenvalue, so you want to look at the like null space of like a minus lambda I to get the like eigenspace. And so I took a minus lambda I and I plugged in 1 for lambda as well. So that's how we got this matrix with zeros on the diagonal now, because we plugged in 1 for lambda. Yeah. So here, whatever your eigenvalues are, you want to take each of them and plug them in for lambda. So here I plugged in 1 for lambda because 1 was the eigenvalue. So like I'll do some other examples so you can kind of see that the full like problem worked out. But then here when we plugged in 1 for lambda, we had to find the null space. So then like ordinarily for finding null space, you would do some row operations to put it into row echelon form. Here it's kind of like already reduced though, if you will. So here what I did is I circled the 2 pivots, which are these 2 ones. Okay. And so the first column was missing a pivot, so I made x the free variable then because of that. Then if you take each of these rows and like convert them into an equation for the null space, this first row is like 0x plus 1y plus 0z, and then you equals 0. That's how I got these two from these two rows and setting it equal to 0 for the null space as well. Okay, all right. Yeah, so this was kind of so I kind of commented that this was like somehow bad last time, but I didn't explain why it was bad, but now we're kind of seeing why it's bad. It's bad because it's not diagonalizable. Yeah. Yeah, so, but I guess like, so a matrix being diagonalizable has many uses. Most of the applications that I've seen are more like theoretical, but it also has some like applications in practice as well. So if your matrix is not diagonalizable, then it's like you can't. It's harder to work with, I suppose, in many applications when that's the case. Okay. Now up here, I did another example last time, which I want to look at real quick. So it was a 3x3 matrix, and this time what happened is it has two distinct eigenvalues, 2 and 4. 2 was like repeated twice. Okay. Now when we looked at the eigenspace for lambda equals 2, it ended up giving us a two-dimensional eigenspace. So we got like a two linearly independent eigenvectors for lambda equals 2. And I didn't do it, but if you look at lambda equals 4, that would give you like a third eigenvector, should be independent of these two. So like this matrix, it would have given you 3 independent eigenvectors. And so this one would have been diagonalizable. Okay. All right. Okay. Now, I'll make a few comments, and then I'm gonna do a couple of examples after that. So I actually kind of hinted at it just now when I was explaining one of the examples. Something that I think is useful to know, though, is that the eigenvectors that correspond to distinct eigenvalues are going to be linearly independent. Okay? They are if they correspond to distinct eigenvalues. Okay? So when I was saying that in this example, when you get the eigenvector corresponding to lambda equals 4, it would be independent of these two. And that's because these two correspond to a different eigenvalue. So if the eigenvectors correspond to like different eigenvalues, then they're going to be sort of like automatically linearly independent. And as a corollary of this theorem, so like a consequence of it, if your matrix A has n distinct eigenvalues, then it is going to be diagonalizable then. Because with those n distinct eigenvalues, that will guarantee that you have n linearly independent eigenvectors. Okay. And then what I was kind of pointing out in the two examples I was referencing from last time, if your matrix does not have like n distinct eigenvalues, so if one of them is repeated, it may or it may not be diagonalizable. And the only way to know is to just find the eigenspaces to see if you have the n linearly independent eigenvectors or not. Okay. Okay. Let's take a look at an example right now. Just checking whether a matrix is diagonalizable. And if it is diagonalizable, to then like work out what the matrices X and capital lambda would be. Okay, so here's a matrix that we can look at. Okay. So we're going to check if it's diagonalizable. And then if so, when I find these matrices X and lambda, so that A would factor as X, lambda, X inverse. Okay. And so essentially this problem will boil down to finding the eigenvalues and then also the corresponding eigenspaces. Okay. So we're just going to work through that first. So working on the eigenvalues right now. We first want to compute the determinant of A minus lambda I. Okay. Okay. I guess I'll just set it up. But now that I'm looking at this matrix, I wonder. Okay, so remember that for A minus lambda I, you just subtract lambda from the diagonal entries of A. And then we need the determinant of this matrix. So to compute the determinant, I typically just do like a cofactor expansion. So let's say I will do cofactor expansion just along the first row, okay? So I would take 2 minus lambda times, and then remove that row and that column. I need the determinant of this remaining 2 by 2. And then next we would do minus the -1 times, and then remove that row and that column. We need the determinant of this remaining 2 by 2. And then lastly, it's going to be +1 times remove the row and the column containing that one, and then we need the determinant of this 2 by 2. Okay. So then we will work out each of these 2 by 2 determinants next. So for a 2 by 2 determinant, remember it's AD minus BC. So we'll do 2 minus lambda times 2 minus lambda. So I guess I'll maybe follow that out in the next step. And then we're going to do minus a negative 3, so plus 3. This one, I guess that's going to be plus. And then doing this determinant, it'll be negative 3 times 2 minus lambda. Let's maybe distribute that, so it'll be negative 6 plus 3 lambda. And then we're going to get minus a positive 9. Okay. For this one here, determinant will be negative 3 minus these two multiplied together. So it'll be minus a, if I distribute, it'll be minus negative 6 and plus 3 lambda, like that. And let me see what we have out here first. So this is negative 3 plus 6 minus 3 lambda. So we have like minus 3 lambda plus 3 altogether from that. This is 3 lambda minus 15, it looks like. So 3 lambda minus 15. Over here, let's pull this out and let's kind of see what it gives us. So that's going to be lambda squared minus 4 lambda plus 4. And then we have that plus 3 as well. So lambda squared minus 4 lambda plus 7. Okay. Okay, let's see here. And then I don't see anything particularly nice I can do just yet. So I think what I'll continue doing is just I'll go ahead and multiply the rest of this out and just sort of combine like terms, and then we'll try to see what we can do with the end result. Okay. Yeah, I don't really see anything I can factor right now, so I'm just going to multiply it out. Okay. So here we'll get 2 lambda squared minus 8 lambda plus 14 minus lambda cubed plus 4 lambda squared minus 7 lambda. And then out here, the 3 lambdas would cancel at least. 3 lambda minus 3 lambda. And we have this minus 15 plus 3, so I guess that's a minus 12 altogether. Okay. Yeah, so let's combine like terms. We have the negative lambda cubed. For lambda squared, we have 2 plus 4 gives us 6 lambda squared. Minus 8 minus 7 is minus 15 lambda, right? And then we have 14 minus 12 gives us a plus 2 at the end, okay? Yeah, that's right. So as I talked about last time, when you compute determinant of a minus lambda I, so it's going to be like a polynomial in lambda is what it's going to turn out to be. For our n by n matrix, it'll be like an nth degree polynomial. So in this case, it's a cubic polynomial for a 3 by 3 then, okay? So we want to, for the eigenvalues, you set this equal to 0 and try to find the roots to get the corresponding eigenvalues, okay? So here, since we're setting it equal to 0, I'm just going to multiply everything by negative real quick, just because it kind of looks nicer to not have a negative in front of the lambda cube term. All right, and then here we want to see if we can factor what we have. Yeah, let's see here. Yeah, let me think about it for a little bit. Okay, let me see. So I'm not too sure if it works out super nicely. Okay. So when I get to a situation like this and I don't really see how to factor it, what I tend to do is I just tend to sort of start like guessing a few possible roots. Okay. I can talk a little bit more about that, but I guess for now, I think if you plug in 2 for lambda, that everything will zero out. So like 2 would be a root of this. So let's just kind of confirm that if I plug in 2 for lambda. That's going to be 8 minus 24 plus 30 minus 2. And minus 24 plus 30 is 6. Oh, not quite. It's 6 plus 6, right? It's 12. So that doesn't work. Okay. Yeah, okay. I might have messed up this example. I was a little bit hesitant when I first started this example because so I try to create my examples ahead of time. And what I tend to do for eigenvalue, eigenvector problems is, I kind of start with, I want these to be the eigenvalues and these to be the eigenvectors, sort of. And then I create the matrix A out of that. I have a sense that I miscopied the final result, though. And I don't remember what the final result was. So, so normally what I would do is, in a situation like this, which can happen, it's not necessarily the case that this will always be easy to factor. What I tend to do is I tend to guess one of the roots, And the way that you can figure out like what numbers to guess is if you see here, find the factors of the constant term. So in this case, our like constant term in the polynomial was the -2. If you get the factors of that constant term, those are the possible integer roots of the polynomial. So for this polynomial here, the possible roots would have been possible integer roots. Would have been factors of -2, which would have been plus or minus 1 and plus or minus 2. But when I check it, I think these aren't going to be roots, meaning that it doesn't have integer roots, or at least it doesn't have like 3 integer roots. This is what we'd want for an example. Okay. So I think I will abandon this example then. So we'll take a look at another example instead, okay? I guess I probably shouldn't have looked at this example to start with. I had a feeling that something was off at the start already, that I might have miscopied it, but I was hoping I didn't, but I think I did, yeah. Yeah. Here's another example. I was hoping to do something different with this example, but I guess I'll use it for this though right now. Okay. Okay, sure. Well, let me think. Let me look at what all I want to do today now at this point. Okay, I'll tell you what. So instead of doing this example, I'll skip to another one that I have as well, because maybe this will tie into what I want to talk about later as well. So let me jump to this matrix over here. And for this one, we'll go ahead and check if A is diagonalizable. And then, again, if so, we want to find the matrices X and capital lambda such that A will factor as X times capital lambda times X inverse, okay? All right, so this example should work out more nicely. So for these problems, you do just want to start by finding the eigenvalues and the corresponding eigenspaces. So to get the eigenvalues first, you want to do determinant of A minus lambda I. Okay. So A minus lambda I, that's going to minus lambda from the diagonal entries of A. Here to compute the determinant, so again, I'll do cofactor expansion. So actually, this one's easiest if I do cofactor expansion along the second row or the second column, because those are the rows or columns with the most zeros in them. if I just expand along the second row, we'll have a 0, and then we'll have plus 1 minus lambda times, if I cross out the second row, second column, we have this remaining 2 by 2, and I need the determinant of this. And then we'll have a like plus another 0 after that. Okay. Okay, so that was cofactor expansion along the second row is what I did just now. And then if I work out this 2 by 2 determinant, so we're going to get 1 minus lambda squared minus 1. Okay. And then let's set that equal to 0 now to find the eigenvalues. Okay. Okay, so one possibility is that lambda equals 1, so that's one of the roots. The other possibility is for everything here to equal 0 instead. So let me move the 1 over. And then let me sort of square root both sides. So there's two possibilities. We're going to get 1 minus lambda could be plus or minus the square root of 1. Let's multiply both sides by negative. So lambda minus 1. And here, when you multiply by negative, it's still two possibilities of plus or minus 1. And then when you add 1 to the other side, so it could be 1 plus 1, or it could be 1 minus 1, which should be 0. Okay. Okay, so for this matrix then, it has eigenvalues of 1, 2, 0. Okay. And then now that we have the eigenvalues, so first, with this we can answer whether or not A is diagonalizable, actually, before we get the eigenvectors. So this matrix, 3 by 3 matrix, and it has 3 distinct eigenvalues. So having 3 distinct eigenvalues does already guarantee that it'll be diagonalizable. Okay. Okay. Now to finish up the rest of the problem, though, you would still need to find the eigenvectors, though. So we'll do that next. So I'll just take each of these eigenvalues. I'll start with lambda equals 1. Yeah, so here it's like the way that you order is not too important. Okay. So I'll just pick the first eigenvalue that I have written down. So I'm going to plug 1 into this matrix here. And you want to find the null space of this matrix to get the corresponding eigenspace. Okay. So this matrix is already pretty much reduced, if you will. So for the null space, if I just take these two non-zero rows, this first row gives us an equation like z equals 0. The third row gives us like x equals 0, if you will. So in this case, x and z are 0, and then y is going to be the free variable this time, since the second column is missing a pivot. So that's going to give you like a 0, t, 0. for the eigenspace, or if you factor out the t, 0, 1, 0 would be like the basis for the corresponding eigenspace. Okay. And so for the purpose of diagonalization, we only need the basis for each of the eigenspaces. So let's make a note that we have the eigenvector 0, 1, 0 for lambda equals 1. Okay. Let's look at lambda equals 2 next. So when lambda is 2, so we plug in 2 for lambda, a minus 2i will be -1 on the diagonal this time. Okay. And then again, you want to find the null space of this matrix now to get the corresponding eigenspace. So maybe here, if we do a few operations real quick, if we just do maybe row 3 plus add row 1 to row 3, I see that gets us a row of zeros. And then this is a pretty reduced, I think this is a good enough place to stop. Well, I mean, it's not a big deal, but you could maybe multiply row 1 by -1, multiply row 2 by -1 as well. So that's just kind of if you kind of want the like reduced row echelon form. So you want to get like a +1 as the pivot, but that's not too important. Okay. I guess like in either case, you'd want to like, at least what I would do is I would write out the corresponding system of equations now. So like here in the first row, you get like x minus z set it equal to 0 for the null space. Second row will give you y equals 0. Okay. And in this case, these would have been the pivots. So we would choose z to be the free variable. So then we have y is 0, and if z is t, then x is equal to t as well. And if you were to like factor the t out from that, you've got the vector 1, 0, 1. So this would be like a basis for the eigenspace for lambda equals 2. Okay. And then I guess the last thing we need to do is also look at when lambda is equal to 0. So if you just replace lambda with 0, it's it's the original a, right? Yeah. Yeah. Okay. And it's not a big deal, I guess. Row 3 minus row 1 gets us the row zeros. And then that's already reduced row echelon form, actually. Okay. So we'll write out the equations that we get from that. Again, here we would probably choose z to be the free variable since the dirt column is missing a pivot. So it's almost the same as what we did just now, but x is going to be negative z. So x would be negative t in this case. Which will ultimately leave you with -1, 0, 1 as a basis for this eigenspace for corresponding to like lambda equals 0. Okay. Okay. So now at this point, now that you have all the corresponding like eigenbases, if you will, to like write out this like factorization of A, you need to construct these matrices X and capital lambda. Now, if you remember, X is supposed to be a matrix of eigenvectors of A, and lambda is just supposed to be diagonal with the eigenvalues on it. So all we'll do here is we'll take the 3 eigenvectors that we found, put them into matrix X as columns. Capital lambda is diagonal with the eigenvalues that we have on it. Okay. And then with these 2 matrices, so this matrix X should be invertible, and you should have this factorization that A will be X times capital lambda times X inverse. Okay. All right. Now, so regarding like the way that you order the eigenvalues and eigenvectors, so it doesn't matter as long as the ordering that you use in each of them like matches. So for instance, like if you chose to do like for lambda, instead of like 1, 2, 0, if you chose to do 0, 1, 2, for instance, in that order along the diagonal, you would just have to adjust your X so that its first column would have to be the eigenvector corresponding to lambda equals 0, right? Likewise, the second column of X should be the eigenvector corresponding to lambda equals 1. Okay. So yeah, the order doesn't matter as long as you're sort of consistent with the ordering in both your X and your lambda. Okay. All right. Okay. So I didn't quite do as much as I wanted to do in this review, but that's okay. So in the couple of minutes I have remaining, I'll move on to, well, I'll say maybe, that's right, yeah. Okay, so first I want to mention one of the applications of diagonalization, okay? So diagonalization makes it relatively easy to compute high powers of a matrix. Okay. So if you wanted to take a matrix A and raise it to like a high power, like A to the power of like 50, this is like saying take the matrix A, multiply it by itself 50 times. Yeah, that's what A to the 50 would be, okay? So if you think about how matrix multiplication works, then you can kind of imagine this is a pretty tedious process. But if your matrix A is diagonalizable, it turns out to be a lot simpler. So to see how this works, so if A is diagonalizable, we have this factorization. A is x lambda x inverse. Now, notice that, so what I'm going to do is I'm going to compute a squared just to illustrate something. So if I compute a squared as a times a, and then I use the fact that a is x lambda x inverse, okay? So here we have a squared, it's a times a. You'll notice that in the middle, this x inverse will actually cancel out with this x. So that's going to leave you with x times lambda squared in the middle, and then times x inverse at the end, okay? And I did it with a squared, but you can kind of generalize it, so a to any power k. If you work it out, it'll be x times lambda to the k times x inverse in general, okay? And for diagonal matrices, when you raise them to a power, and you do like the actual like matrix multiplication, it turns out that it's equivalent to just raising each of the diagonal entries to that power. So like raising a diagonal matrix to a high power is comparatively easy. And if your matrix is diagonalizable, then you can exploit that factorization to get a relatively easy way of computing a high power of your matrix, okay? So then just kind of like as a small illustration over here. So let's say that given the original matrix A that we had, and if we wanted to raise this to like a somewhat high power, let's say to a power of 10, we could do that by taking the factorization that we have here with the x and the lambda, and to compute a to the 10th power, we would just need to raise lambda to the 10th power in the middle. And then I never computed x inverse, but it's not too hard to compute. I'll leave it like that though as I'm writing it out, okay? So then I guess in this case, 0 to the 10th power, 0, 1 to the 10th power is 1, and I know 2 to the 10th power is 1024. So if you just like multiply these three matrices together, that will give you like 8 to the 10th power is the idea, okay? Okay. The last thing I wanted to talk about today, I'm kind of out of time. Okay, I guess I know I'm going to have one more review next week as well, so I'll save what I was going to talk about for that. Not too sure, nope. Yeah. I guess what I'll do is I'll end my review with kind of just like a kind of one-off example of sorts. Okay. Okay, so like I said, it's kind of a one-off example. But I think I saw a couple of questions on some of your assignments that started with this, I guess. There might have been like a question like on your homework assignment and then like another one in your practice problem set that you had in e-learning. But they give you a matrix and they would ask you to like, verify that certain vectors are eigenvectors. So for this example, I'm going to say verify that these two are eigenvectors of A. So I guess what I wanted to kind of call attention to this is the simplest way to do this, I would say, is to actually just resort back to the original definition of eigenvalues and eigenvectors. We haven't made use too much of that original definition, but the original definition was like A times X should be lambda times X. So what you'd want to do for these types of problems is take matrix A, multiply by each of these vectors. We'll start with the vector 1, 1, 1 first. Yeah. So yeah, so if we do the multiplication of this, -1 plus 6 minus 4, I think is 1, right? -4 plus 9 minus 4, yeah. -2 plus 2 plus 1, okay? So we have A times this first vector equaling like the scalar 1 times that vector, okay? Because 1 times 1, 1, 1 gives you 1, 1, 1, okay? So that means that this 1, 1, 1 vector is an eigenvector, and it has corresponding eigenvalue of lambda equals 1, okay? Likewise, I can take this matrix and multiply with the second vector that was given. And if we work this one out, see here, -1 plus 6 minus 4. Is that 1 again? Okay. And then oh wait, no, never mind. I was doing, so -1 plus 6 plus 0, because the last one is 0. That would be what, 5, right? And then here, -4 plus 9 plus 0 is 5 again. -2 plus 2 plus 0 is 0. So A multiplying this vector, 1, 1, 0, gives you 5 times 1, 1, 0, 5, 5, 0, okay? So like this was also an eigenvector then, and its eigenvalue was 5. Okay? If you wanted to find the last eigenvalue of A, so there's no need to do like the determinant of A minus lambda I, although you could do that. But you could also use one of the facts that I mentioned last time, which is that the trace of your matrix should equal the sum of its eigenvalues. So last time I talked about how the trace of a matrix, so the trace is the sum of the diagonal entries. Yeah, so the trace of A is the sum of the diagonal entries, okay? And that turns out to also equal the sum of the eigenvalues. Now, for a 3x3 matrix, you should have a third eigenvalue is what's going on, okay? So, yeah, knowing two of the eigenvalues, you can use the trace to figure out the third one. So then the third one would be lambda equals 3 in this case, okay? Right, right. That's right, yeah. So if only one is missing, then using the trace would be the kind of the best way I would say to figure it out. That's still okay. Oh, I see what you're saying. Yeah, yeah. Right. Well, so I talked about it last time, but for this equation to work, if one of your eigenvalues is like repeated, you would like add it. You would repeat how many times you're adding it in the sum. Right. Yeah. So I had an example last time. Let me jump to that real quick. For this one, actually, yeah, perfect. So this is one where you had to repeat it. Well, it was diagonalizable though, but I guess if I look at this matrix then. So this one's not diagonalizable, okay? But its trace is 1 plus 1 plus 1. And the sum of its three eigenvalues would be like 1 plus 1 plus 1. Okay. So if an eigenvalue is repeated, you have to add it that many times for this part. 2 was an eigenvalue repeated twice. So I had to add it twice when I was doing the sum of the eigenvalues. And when I did that, then the sum did match the sum of the diagonal entries. Okay. Okay. I guess as a quick comment as well. So the trace is the same as the sum is equal to the sum of the eigenvalues. I also mentioned last time how the determinant turns out to equal the product of the eigenvalues. Again, for this one though, if an eigenvalue is repeated, you have to include it that number of times in the product. Okay. Yeah, so for the eigenvalues, if they are repeated, then in these cases where you're thinking about the sum and the product to match the trace and determinant, you have to include the multiplicity, if you will. But like when you're finding the eigenspaces, though, you're not going to do like lambda equals 2 like twice, for instance. When you're finding the eigenspaces, because you know, so like for lambda equals 2, plug it in and find the null space, and that's all you would do, right? So you can't like plug lambda equals 2 again and then expect a different outcome, you know? Yeah, yeah. So for the eigenspace, you don't have to do it like twice, but for this kind of thing with the trace and the determinant, you want to include the multiplicity for that, okay? Yes, yeah, yeah. Yeah, typically I would say yeah. And I guess maybe just the last thing in this kind of example that I was looking at, since we found this eigenvalue, we could also find its corresponding eigenspace now. You would just do like A minus 3i and find the null space of this matrix to get the corresponding eigenspace. Okay. So A minus 3i, you would minus 3 from each of the diagonal entries. And then for this one, you would do a couple of row operations probably to find a null space. Okay. All right, but I guess let's wrap things up with that. So I just wanted to kind of comment on this problem. And so I didn't want you guys to like do it by just like doing determinant A minus A into I and whatnot. Like you could do that and it would work, but to me, that's not what you should do though. Okay. Right. Okay.